My name is Efrain Ibarra Jimenez. The name of the presentation is Novel Nonlinear Control Method for First Order Systems and its implementation in a temperature system. The topics that we are going to try in this presentation are the following: problem statement, main contribution, development theory for open loop control and closed loop control, simulations and implementation in a temperature system. Problem statement. Among the existing control theories for linear systems, the transfer function concept is commonly used in the design of the industrial controllers, since the location of the poles and the definition of the type of stability and solution are easily known. Therefore, for a linear differential equation, zero initial conditions are always assumed. However, this not always applies to all systems. In addition, the output response is usually analyzed using an input control as the unit step, mainly because it is easier to obtain an analytic solution and the setting time when the solution is close to the reference at 98%. For this reason, it is necessary to establish a theory that contributes the proximity to the design reference and to be able to control the slowdown or acceleration of the output response. In this work, the main purpose is to develop a generalized nonlinear control theory that can be used in a first-order differential equation system for solving all the trajectory tracking problems, both for constant and time-variant references, and considering any initial condition. Main contribution. The main contribution of this paper is to introduce a new control design method for a first-order differential equation that guarantees the following points. Number one, the output signal response can follow constant or time-variant reference. Number two, the initial condition for a first-order differential equation can be selected with freedom, implying that the transfer function is no longer necessary, since this concept limits the realism of the physical systems by considering that the initial conditions are always zero. Number three, analytical solutions are found for tracking constant and time-varying references, which makes it possible to avoid using any numerical methods. Number four, a closed-loop control formula is obtained for tracking constant or time-varying references. Number five, the designed controllers allow for acceleration or deceleration of the convergence rate to the desired reference. Number six, the controllers can be automatically tuned to allow the desired reference to be raised with a small error and achieved in a finite time, which can be proposed to our liking, where this fact is defined in our article as the percentage convergence. Eventually, the goal is to use this developed control theory to design temperature control and verify its effectiveness in approximate real-time implementation. Control theory designed for a first-order differential equation. Between the developed theory, we can find two different kinds of controllers, the open-loop control and the closed-loop control, where the main differences will be described. Open loop control. Consider the first order differential equation given by expression number 1. Then, to guarantee the tracking to a time-varying reference R of t, it is necessary to introduce the following theorem. Theorem number 1. For the system number 1, proposing the controller U of t given as this expression, with known references R and R dot, its solution is given by this expression. And we will have that the solution approaches to the variant reference when the time goes infinity, only for values of a higher than 0. To prove theorem 1, the control U is substituted into system number 1, obtaining the following first-order differential equation in terms of the error, where we have the initial error, where Ex of t corresponds to the difference between the solution and the desired reference, and this expression corresponds to the derivative of this error. Now, applying the Laplace transform to system 2, we obtain the following expression given by 3. Then, to obtain the solution in error terms, we need to apply the inverse Laplace transform to system 3, obtaining the error solution given by expression 4, where we have the initial error times the exponential of negative at. And remembering that the error is given by the difference between the solution and the desired reference, we have the solution x of t is equal to r plus some initial error times exponential of negative at. And if the parameter a is higher than 0, then this exponential goes to 0 when time increases. Therefore, we have proven theorem 1. Note that u of t given in theorem 1 does not have a dependency on the solution. So, u of t is an open loop controller that can be written as equation number 5, where the first will serve for tracking variant reference, the second for tracking a constant reference, where the above controllers given in 5 guarantee the tracking of the references only if a is higher than 0. Closed loop control. Now, in order to control the system 1 for any constant parameter a, and to make that the solution tracks any reference, we introduce the following theorem, theorem number 2. For the system 1, proposing that the control is given by this expression with k lower than a, and with no sign and references r and r dot, we obtain that the solution will approach to the variant reference when the time goes to infinity. Proof. For proving theorem 2, u of t is substituted into system 1, obtaining this first-order differential equation in the error dynamics. Now, applying the Laplace transform to 6, we obtain expression number 7. And applying the inverse Laplace transform to 7, the solution ex of t is given as expression number 8. And remembering that the error is given as the difference between the solution and the desired reference, the solution x of t is given as expression number 9. As in the hypothesis, k is lower than a means that a sub m is always higher than 0, implying that the negative of a sub m is negative. As a consequence, the exponential goes to 0 when the time goes infinity. Hence in 9, we have that x approaches to the reference when the time goes infinity. Therefore, we have proven theorem 2. Also, observe that the reference is constant for all time, then the derivative of this reference will be 0 for all time. And implying that in this theorem, the controller will be given by this expression. Now that u of t given in theorem 2 has a dependency on the solution, so u of t is a closed loop controller that satisfies the following. Here we have this control that will serve for tracking a variant reference, and this will serve for tracking a constant reference. In both cases, the convergence to the reference can be speed up or slowed down, because in the solution 9, the parameter a sub m that is positive can be modified with different values of k, implying that the exponential term decreases to 0 quickly or slowly, depending on the choice of k. The generalized setting time Ts. Now suppose that we have selected some k lower than a, and according to theorem 2, the solution approaches to the variant reference, when the time goes infinity. However, if I want to estimate the time Ts when the solution x of t is very close to the reference r of t, consider the general solution in terms of the error given by this expression, and suppose that for some time t equal to ts, we have the following, given in 11 equation. The above implies that the exponential will be given by this expression when this is evaluated in this time, in the ts. And when applying the logarithm for both sizes, we obtain equation number 12. Hence, equation 12 represents the necessary time to reach the percentile of the initial error between x sub 0 and r sub 0, and Ts is called the generalized setting time. Approaching the desired reference. To determine how close the solution is to the reference r of t at time Ts, notice that according to 10, this expression will be fulfilled, and then we will have that approaching to the variant reference in this time will be given by 13. And if the variant reference is constant for all time, this will be fulfilled, implying that the approaching to the constant reference will be given by 14 expression, where 13 and 14 indicate how close the solution is to the reference at time Ts. And selecting an adequate percentage, the time Ts can be modified supposing distinct values of k. In addition, for a desired setting time, we can find a unique value of k, so that 13 and 14 are fulfilled. This means that k will help auto-tune the reference rate of convergence. Now suppose that we have selected some percentage and a desired setting time td. Therefore, we obtain 15, where the first represents how the solution is so close to the variant reference and in this desired setting time. And the second represents how the solution is so close to the constant reference in this time, in this setting time. In addition, satisfying 15 in a finite time TD implies being able to speed up or slow down the rate at which the solution x of t approaches the reference. Hence, to indicate the approximation, expression 15 is called the percentage convergence. Convergence gain k. The gain k will serve to design controllers that speed up or slow down the convergence rate to the desired reference. This means that k must guarantee that the percentage convergence given in 15 is fulfilled. In order to find k, we use the equation 12, obtaining that am is given by this. And therefore, k given in 16. Taking 16 into the closed loop controllers u of t given in 10, we have the following. We have expression 17, that is a controller that guarantees the percentage convergence shown in 15 for variant reference r of t. Loop control formulas. In this time, we have the setting time Ts for different percentages, where this table will be useful to obtain all the closed loop control formulas for tracking variant reference, given by expressions 18a to 18c, where this controller will satisfy the percentage convergence for a variant reference. In the case when we have a reference constant, this will be 0. Simulation example using a closed loop controller. Example 1. Consider the system given in 19 with a reference r of t given by this expression. Therefore, to achieve the percentage convergence given by this equation, in a desired setting time td, we will use the closed loop control 17, and with percentage equal to 0.7%, implying to use the control formula 18b. And with setting times td equal to 10 and td equal to 25, we obtain the following controllers, 20a and 20b. Following with example 1, the figure 1 shows that the solution x of t approaches to the reference r of t, and observe that the percentage convergence is fulfilled in the respective setting times td. Here are shown here and here, when the controllers 20A and 20B are applied to system 19. Likewise, figure 2 shows the controllers 20A and 20B. Simulation example for tracking high-frequency reference using a closed-loop controller. Example number 2. Consider the system given by this equation with parameter A equal to dot 3 and initial condition -2. To visualize the dynamic behavior of the solution tracking high-frequency references, the closed-loop control U of t given by this expression is designed, considering tables 3 and 4. To fulfill the percentage convergence given by this equation, we propose that the percentage is given by this, with a desired setting time of 4 seconds. Therefore, the controller U of t necessary for tracking each reference is given as follows. Thus, when we apply controller 21 to the system, the solution x of t tracks the desired reference with high frequency intervals, as seen in figure 4 and 5. Algorithm for tuning the convergence gain K and the closed-loop controller. Practically, we have to follow 6 points to guarantee the perfect tuning of the closed-loop controller. Temperature control system simulation and implementation. The system is closed, and in this case the liquid is water, and the heat transfer occurs by convection. Therefore, in order to obtain a first-order differential equation in terms of the temperature of the liquid, we consider that the external temperature Te and the liquid temperature Tr are measurable. Then we have also considered the equations 22 and 23. When substituting 23 in 22, we can obtain the following expression given in 24. Then, simplifying the above equation, we have the following expression given in equation 25. Finally, we can obtain, doing a better simplification, we obtain 26 equation, that this will serve to design the thermal controller given by QA. Now, to use the control theory previously developed and according to the algorithm presented previously, the first step is to make system 26 take the form of system 1. To achieve this, suppose in 26 that the thermal control QA is given by this expression. Thus, we will obtain the following, where we have in the system 27 the virtual control U of t. And with the following parameters, with A higher than 0, we are in condition to design the virtual control U of t using a closed-loop controller. In addition, using table 2 with TD as constant reference, we have the following expression 29, where this is the percentage convergence for a constant reference. Then, according to theorem 2, with 20A in 27, the solution will be given by 30. To know the source heat QA of t that needs to be supplied to the tank and guarantee the percentage convergence given in 29, the virtual control 28 is substituted for this expression, obtaining the equation 31. For this simulation, we suppose that the setting time is given by 600 seconds, the initial temperature 25 degrees Celsius, the external temperature as 32 degrees Celsius, and the desired temperature as 90 degrees Celsius. For the application of the developed theory in the physical prototype of this work, follow the next algorithm. Results and discussions. The design of a novel nonlinear control method theory for first-order systems was property, as seen in the simulation results. Moreover, in the implementation prototype, the septem blue color signal versus the real-time as red color signal is shown in Figure 11. Other results and discussions can be consulted and read on this slide. Conclusions and future work can be consulted and read on this slide. Thank you very much for your attention.